Hi, everybody, and thank you for coming out to our talk today on Mayfly. Mayfly was built by a team of remote developers. I'm Zach Kerner. On behalf of my colleagues, Joshua Lindsay, Steve Price, and Nate Shu, we will hear from them shortly. Mayfly is an open source tool for deploying high memory, high compute apps to the browser. Mayfly uses a technology called session backends to overcome the low compute, low memory limits of the browser. Session backend is a dedicated service that offloads computational power from the browser to a virtual machine or container orchestrator. Before we say more on session backends, I'd like to start by introducing our problem domain. We're going to talk about two types of high memory, high compute apps. There are apps with resource intense graphics like data visualizers. And there are apps with complex data structures that need to be updated frequently. One example of this is a code editor. First, let's take a step back and start with a type of application I'm sure most of us are familiar with: create, read, update, delete, or CRUD applications. CRUD applications depend on relatively simple data structures. Take a banking app as an example. If the user wants to deposit their paycheck, the app creates a new transaction and updates the user's balance. The app does not need to know the user's entire history of deposits and withdrawals. This process is called a change in state. State change in a banking or any CRUD app is small and simple. It does not generate a lot of data. The user enters a deposit amount and we change their account balance. But let's say the application is a code editor and not a banking app. Code editors rely on complex changes in state to maintain low latency. Code editors depend on a data structure called an abstract syntax tree, which is a hierarchical representation of a code's structure. The code editor needs to consider relationships between parts of the entire file and not just one or two lines of code in isolation. Unlike the CRUD application, complex changes in state are carried out frequently. This generates a lot of data, often too much data for the browser to handle. So before browser-based hosting, most developers deployed their high memory, high compute applications to the desktop through a standalone app. When it comes to performance, there are many advantages to a desktop app. Desktop apps are engineered to fully utilize the native hardware of the host machine. A desktop app can make direct use of the central processing unit, the CPU, and graphical processing unit, the GPU, of the host hardware. They are designed for the specific operating system of the user. There's an app for Windows and there's an app for Linux. Desktop apps are not subject to the same security and sandbox restrictions as web applications. The desktop apps are more performant than browser-based apps, even on the same machine. Desktop applications come with certain downsides. They have to be downloaded, which takes time. Some users may give up and use a competitor's application instead of taking the time to download and configure your app. If the user wants to access the app on their phone or some other device, let's say a work and a home computer, they need to download the app again. With desktop applications, there's a lot of waiting around and inconvenience, which explains why developers have turned to browser-based hosting. So how can developers manage the surge of data coming from these apps? What sort of browser technology is available to them? One approach is to use cookies. Cookies are a universal feature of browsers. Another approach would be to use built-in storage technologies like local storage or indexed DB. Unfortunately, none of these approaches are sufficiently robust. Cookies are capped at 4,096 bytes of data per cookie. So a developer would have to break up state data into thousands of cookies, then reassemble that data with each request. Another approach is to use JavaScript libraries and APIs to make changes to the DOM. The DOM is a tree-like representation of the web page. Among the more famous JavaScript libraries is React. React manipulates the virtual DOM, which is a lightweight copy of the real DOM, and only makes changes to the parts of the DOM where state has been altered. This saves on redundant reloads and leads to smoother performance. React, however, will run into scaling issues when state becomes too complex. The last approach we'll look at is data compression. For this, developers may turn to a technology called WebAssembly. WebAssembly compiles a number of high-level languages, Rust, C++, into binary. This greatly decreases the amount of data sent with each request response cycle and enables developers to move state data from the server to the client. With WebAssembly, we can host our high compute, high memory apps in the browser, but, and here's the kicker, we would still need to contend with the constraints of hosting directly in the browser. We're in search of a more performant alternative that allows our users to access our app through the browser while we, the developers, host that app off of the browser. Session backends are a technology for hosting web applications on hardware with superior memory and CPU. Session backend is a dedicated service spun up on demand by an orchestrator to maintain complex state in high memory, high compute apps. Session backends are exposed to the internet through an endpoint, typically a URL. Session backends can host a wide variety of applications, from collaborative apps to data visualizers and 3D animators. Session backends are agnostic to their execution environment. They can be deployed on a virtual machine, as a container instance, or as a process in Rust. Session backends accomplish this by adopting stateful system design. Stateless design is the standard for low memory, low compute applications like the banking app from earlier in the presentation. In stateless design, client requests can be carried out by any server in the application's web tier. My request can be carried out by the New York server today and the New Jersey server tomorrow. There are no permanent client-server assignments. In a stateless system, there is no memory or history, hence the goldfish. Obviously, a banking app has to keep track of the identity of the customer, but it does not need to know about past transactions. In a stateful system, this is all reversed. Client-server connections are unique. Clients are connected to the same server every time. It's like your guidance counselor in high school, freshman year, sophomore year, you're with the same guidance counselor. The guidance counselor remembers not only your name and address, but they also remember your face, your extracurricular activities, and your detentions. I, of course, am not speaking from experience. In stateless design, we send metadata to give context to each request. Metadata is used by the system to identify the client so that it can update the correct account balance. In stateful design, context is already present, so there's no need to send metadata. CRUD apps, like our banking app, are built around stateless design. This is the traditional architecture for web applications. In stateless design, much of the data is stored on client hardware. As data increases, client hardware is put under strain. Session backends help to solve this problem by adopting stateful design. Since requests carry a lot of data, it makes sense to store that data on the web server instead of on client hardware. Every decision in system design comes with trade-offs and drawbacks. As the chess great Bobby Fischer once said, you have to give squares to get squares. Stateful design has the advantage when it comes to dealing with high data throughput. Stateless systems, on the other hand, are easier to scale. You can add servers when demand is high. You can take away servers when demand is low. This is not so in a stateful system where clients need to be directed to a specific server. It follows that failover is easier to manage in a stateless system. In stateful design, we need to make sure our new server is preloaded with all of the contextualizing data that was stored in the old server. That, as you can imagine, is not a simple task. Now I'd like to pass the baton to my colleague, Josh Lindsay, who will explain some high-level concepts and challenges in the implementation of session backends.
Thank you, Zach. Zach did a great job explaining why we need session backends, but how do we implement session backends? Our team found that to implement session backends, developers need to address 3 domains in the deployment infrastructure: computation, orchestration, and communication. Computation speaks to the challenge of provisioning compute power to handle high data throughput. The compute space you provision will vary depending on your application's needs. Session backends run on dedicated hardware that does not depend on your browser's resources. Companies have taken various approaches to run their applications on dedicated hardware. For example, GitHub Codespaces provisions a virtual machine for each Codespace instance. You can see in this diagram that GitHub hosts the Codespace in a Docker development container and allows you to choose the number of CPU cores and the amount of memory and storage. Figma takes a different approach. Figma has a fixed number of servers and workers per server. You can see in the green text on the right that Figma provisions a separate Rust process for each active user document. Having a separate process per document allows Figma to handle even the most resource-heavy documents without slowing down other documents in the same worker node. In summary, the computation layer for session backends reflects the need for concurrent CPU and memory resources for every user's session. Now we turn to the brains of session backends, the orchestration layer. Orchestration refers to the on-demand creation and termination of session backends. An orchestrator must spin up a session backend on command and spin down the session backend when the user ends their session. We found multiple ways that companies have handled the orchestration of session backends. GitHub, for its Codespaces platform, orchestrates the provisioning of a virtual machine in the cloud for each user request. As you can see on the right, the Codespace includes all the dependencies needed for your project. Once a user is finished, they must stop their Codespace to save on CPU charges. Figma's approach is to orchestrate the creation of a new Rust process per active user document, then terminate the Rust process once the user ends their session. Our last example looks at Agones, an open source dedicated game server platform that runs in Kubernetes. First, a user requests to run a dedicated game server, then the request is routed to the Agones controller seen on the right. The controller orchestrates the request to provision a dedicated game server for the user and fellow game players. In summary, the orchestration layer for session backends reflects the need to orchestrate user requests to newly provisioned resources for their user session, then to orchestrate the termination and freeing up of these resources once the user ends their session. Finally, to tie the computation and orchestration layers together, we need a communication layer to successfully connect users with their session backends. Communication entails routing client traffic to the correct session backend and establishing a persistent connection, kicking off the bidirectional flow of data between client and server. Communication depends on your orchestration layer and the needs of your application. And here are a few examples we found. GitHub Codespaces connects users to their dedicated code space over the internet through the code editor of their choice, such as the VS Code desktop app. Returning to our example of Agones, they use the host port field of the game server container to route users to their respective game servers. Agones uses UDP as its default protocol for connecting a user with their dedicated game server. UDP, or User Datagram Protocol, is aimed at real-time applications like games. UDP, unlike TCP, does not engage in a formal handshake before establishing a connection, as you can see in the slide. The protocol you choose for connecting users with their session backends will depend on the type of application you want to host as session backends. In summary, session backend orchestrators must address 3 layers to host apps as session backends: a computation layer for provisioning resources for dedicated session backends, an orchestration layer for spinning up and down session backends on demand, and finally, a communication layer for routing users to their dedicated session backend over a bidirectional data stream. Now that we know the why and the how of session backends, let's look at what solutions already exist that will enable you to serve session backends to your users. The most familiar commercial solutions come from large cloud providers like AWS. Amazon's Elastic Container Service, or ECS, is a container orchestrator for managing and scaling containers, while AWS App Runner provides a fully managed service for your application. Both services are full of features and easy to set up, but require additional tools to deploy session backends. The most relevant solution for hosting session backends is JamSocket, the first commercial product explicitly positioned as a hosted session backend platform. Suffice it to say, JamSocket provided much of the inspiration for Mayfly. JamSocket provides many features specific to session backends that make JamSocket the default option if you choose a commercial solution for your session backend needs. In total, the biggest selling point behind commercial options is their ease of setup, freeing you to focus on application development. Each solution has its own robust set of features, but once again, JamSocket is the primary commercial solution built for session backends, allowing them to provide tailor-made support for your session backend needs. Moving on from our commercial solutions, if you have the time and resources, you can use a DIY solution to deploy session backends. Kubernetes and Docker are open source platforms that are feature-rich and highly configurable. However, each comes with its own learning curve and needs specific tools and configurations for hosting session backends. Another DIY solution is called Plane, the custom-built session backend orchestrator behind the commercial solution JamSocket. Plane is open source and configurable and provides various features specific to session backends. As with Kubernetes and Docker, Plane comes with a learning curve, including the configuration of a NAT server and DNS, and therefore lacks ease of setup. In total, the DIY solutions, while configurable, open source, and feature-rich, require a lot of effort for setup. However, Plane is the clear choice for the team looking for a DIY solution explicitly built for session backends. And that is exactly what we sought to do with Mayfly. Our open source tool Mayfly is built on Plane, like JamSocket. However, we wanted to build Mayfly to be configurable and open source so that you could host your session backends with a greater ease of setup than Plane. Being built on Plane, Mayfly is of course also built for session backends. And while not as feature-rich as JamSocket, Mayfly provides the essentials for hosting your session backends. In summary, we wanted to stand out from the crowd by providing an open source solution inspired by JamSocket and built on Plain. We prioritized ease of setup, giving developers a tool built for hosting session backends. Now I'll hand it off to Steve, who will give you a deeper introduction to Mayfly.
Okay, thanks, Josh. Hi, everyone. I'm here to discuss what Mayfly is and how we built it. Early in the presentation, Zach mentioned that Mayfly is an open source session backend tool for deploying high compute, high memory apps in the browser. It starts with a developer's application making an API call to Mayfly. When that is received, Mayfly will automatically spin up a Docker container to run a containerized version of that application. A URL is then sent as a response for the user to connect to that instance. This session backend will run until all connections have closed, at which point it will automatically spin down. Let's start by taking a look at how to install and use Mayfly. The first step of using Mayfly is to install the Mayfly CLI. This is done via an npm install command. Next, running the command mayfly lay will guide the user through a series of inputs to configure their specifications. This will lay the eggs of future Mayfly session backends. Once the initialization process is complete, we can then execute the mayfly hatch command, which will provision Mayfly's infrastructure on AWS and provide a URL to access the platform's dashboard. And you can always squish a pesky Mayfly instance if it is ever necessary to terminate it. So now that we have it installed, let's use Mayfly. Here we see the Services tab of our Mayfly dashboard. You might be asking, what is a service? A service is simply a Docker image of an application that will be utilizing the session backends. Mayfly comes with 4 sample services already, but a developer can upload images of any application they are working on that might benefit from the processing power of a session backend. This is the page for adding a new service. Mayfly will need the name of the Docker image the developer wants to upload, and also a display name for the service here on Mayfly. Once this form is submitted, the new service will be listed along with all the others in the Services tab. When you click on an individual service, you'll be brought to a list of all the backends that have been spawned for that service. Primarily, a developer will implement their application to send requests for a session backend whenever one is needed. However, we also provide a button here that will send a request and list the URL below for testing purposes. Now that we have seen how we can use Mayfly, it's time to get into the details of how exactly Mayfly works and how our team was able to put all the pieces together. If you remember earlier, Josh discussed the 3 layers needed for hosting session backends: computation, orchestration, and communication. Let's now take a look at these 3 layers for Mayfly. The computation layer is built around the plain drones. They're the machines that spin session backends up and down as required. For the orchestration layer, Mayfly uses the plain controller to coordinate and schedule drones and ensure all communication is being directed to the appropriate drone. Lastly, the communication layer of Mayfly utilizes a self-hosted DNS server which routes a user to their session backend, as well as a NAT server which aids in the internal communication of Mayfly. But plain NATs, what are they and how do they work? Let's first answer that before going any further. First, we have the controller. This is this dispatch center. It's responsible for accepting external requests for backends and deciding which drone to run them on. The controller is also responsible for routing traffic to the appropriate drone by serving DNS. Next, as we've mentioned, the drones are the workers that run the actual backends. Each drone runs on a virtual machine and is responsible for coordinating with a local Docker instance to run session backends. Also, as a drone is capable of having many Docker containers running session backends at once, It's also responsible for dispatching inbound traffic from NATs to the appropriate container through the proxy. And here we have NATs. NATs is a publish subscribe message bus, which is designed for event-driven distributed systems, emphasizing simplicity and scalability. This made it a perfect choice to use as a communication hub between the controller and the drone. So now that we have some idea of what Mayfly was built around, the 3 layers we see here, let's get into why you're all here, how we built Mayfly. The first step in building a functional product was creating our prototype. We installed Plane on a local machine. Plane comes with sample configuration files, which includes a Docker Compose file. When running this file, it pulls the necessary Docker images for the Plane controller and the drone and gets them up and running. We then created a simple API to communicate with the NAT server. This allowed us to schedule the session backends to run and then receive the URL to the backend once it was ready. Once we had all parts communicating with each other, the next step was trying to automate the shell commands. For this, we went with the npm package execa, which allows us to automate the execution of these commands every time we sent a request for a session backend. However, we quickly learned the limitations of this setup. Some of these limitations include only using the Docker image that the Plane configuration files are built around, the need for execa to run our controller and drone, and also the inability to scale. Nate is here to go over exactly how we overcame these.
Thank you for the introduction, Steve. As Steve mentioned, at this stage, Mayfly was using the Plane CLI to communicate over the NAT server within the JavaScript child process. Using the Plane CLI, however, came with the trade-off of less control. For example, using the Plane CLI left us unable to specify how long a backend could have no connections before shutting down. To solve this, we used a JavaScript client library to connect to the NAT server and send messages across it. This allowed us to cut out the Plane CLI and gave us full control of the NAT's communication. From there, to fulfill the objective of creating a high compute session backend tool, we decided to transition from hosting Mayfly on our local machine to hosting it in the cloud. At the same time, we also wanted to separate the Plane drone onto its own machine, away from the Plane controller and NAT server. This was to prepare to scale Mayfly by allowing multiple drones to connect to the controller. To fulfill these requirements, we evaluated the benefits and trade-offs of 2 approaches. The first was to use a managed service like AWS Elastic Kubernetes Service or AWS Elastic Container Service to host the controller and drone. EKS was attractive because Plane has a Kubernetes-like structure, with the controller as a control plane and drones as worker nodes. To host Mayfly on either ECS or EKS, we would use AWS Fargate, a serverless compute engine for containers, to host the controller, and an EC2 autoscaling group to host the drones. Both EKS and ECS would work to host Mayfly and provide for horizontal scalability. The second approach we evaluated was using 2 AWS EC2s, one to host the controller and one to host the drone. Rather than using services and tasks to manage containers as with AWS ECS, we would use HashiCorp's Packer tool to create custom Amazon machine images. Amazon machine images are snapshots of a virtual machine's file system. Using custom AMIs to launch EC2s allowed our EC2s to have all of the required applications to run Mayfly without any manual configuration. These AMIs could then be automatically deployed using Bootstrap scripts. Compared to using EC2s, using a managed service like EKS or ECS had the benefit of horizontal scalability. However, both of these services were comparatively more technically complex than the second approach. Specifically for EKS, the learning curve for Kubernetes, and for ECS, translating Plane to services and tasks. Ultimately, we decided to use EC2s as this was a better fit for rapid prototyping. Next, we need to upgrade the Mayfly communication layer. The Mayfly communication layer at this point had been using a setting called path-based routing. Path-based routing is a plain configuration setting that creates a unique URL that routes to a corresponding session backend. It does this by appending a UID to the path of the URL. This was good for rapid prototyping, as it allowed us to avoid dealing with the complications of configuring DNS at the outset. However, using path-based routing came with the limitation of only being able to run simple applications. This was because the UID corresponding to a session backend did not dynamically append to all paths at runtime. As a result, only apps restricted to using the root path were able to run. To solve this, we needed to disable path-based routing and instead configure DNS to route to the drone. To do that, we first registered a domain underneath a DNS provider. Then we set the drone and controller to use that domain as their cluster name. From there, we created a wildcard A record to point to the drone's EC2's public IP. This allowed the controller to generate unique URLs with the UID as a subdomain of our registered domain, as shown in the example. This solved the previous limitations of path-based routing by allowing any containerized application to run on Mayfly. With the previous limitations solved, Mayfly was able to spawn session backends and route to them while being hosted on the cloud. From there, the next challenge was to set out to solve was scaling Mayfly. Vertically scaling Mayfly proved to be as straightforward as changing the instance type of the drone EC2 to suit the developer's computation needs. However, when attempting to horizontally scale Mayfly, we quickly ran into an issue in the communication layer. At this point, the logical progression to horizontally scale Mayfly was to simply create more drones, each on its own EC2, and point them to the public IP of the controller. Connecting more drones and spawning backends from them proved to be straightforward to implement in of itself. However, routing to specific session backends on different drones proved problematic. The problem with routing to the drones through the external DNS provider we had set up was that we were using a DNS wildcard A record to route to a specific drone IP. However, the A record for a subdomain can only point to a single IP address at a time. This meant that the A record for the wildcard subdomain was only able to point to a single drone at a time, which meant it was unable to accommodate horizontal scaling. To solve this, we needed to leverage the internal DNS server within the controller to act as an authoritative DNS server, meaning the final holder of the IP queried for. This would allow the URLs generated by the scheduler to route to corresponding session backends within their respective drones. To do this, rather than pointing a wildcard A record of the domain at a drone, we would need to point the name servers of our domain to the internal DNS server of the controller. This would direct all DNS queries towards that domain to the internal DNS server. Implementing this approach posed significant technical challenges. As Plane is relatively new, the documentation was sparse, requiring further digging to correctly configure the DNS server, which proved to have a relatively steep learning curve. Plane is also written in Rust, a language nobody on our team was familiar with. In order to debug this process, our team used many tools and approaches. To begin with, we used Telnet to ping the controller to determine that port 53, which is the default port for DNS that is used by the external DNS provider for name server queries, was open to a connection. Then we used netstat from within the EC2 of the controller. This allowed us to find out that there was a conflicting process on port 53 that needed to be disabled called systemd resolved, which was used to resolve private IP addresses. From there, we changed the name servers of our domain to the public IP of the controller EC2. However, many DNS providers, including the one we used, require 2 name servers before they allow you to change the name servers of the domain. This presented a problem, as we only had 1 DNS server in the controller. We worked around this problem by using the IP of the controller with backname.io, a service that provides the backname.io domain to route to any IP address specified. Iterating on changes, proved to be slow, as DNS name server changes can take up to 24 hours to propagate. This can be somewhat mitigated by using a DNS propagation checker website to confirm if the change is propagated or not. However, even after the change is propagated, port 53 was allowed inbound on the security group for TCP and UDP. System deresolve was disabled, and the DNS server was confirmed to be listening on port 53. The URLs were still not routing correctly. To determine why this was happening, several methods were used to gain more information. Dig and NSLOOKUP DNS queries were continuously used to check if the DNS server was returning the correct information as modifications were being made. Fortunately, Plain provides good error logs, which were used to help parse out the problem. The packet sniffer TCP dump was also used to determine if DNS queries were actually being sent and received. Most important was analyzing the plain Rust code in depth to understand the control flow of the Hickory DNS server, as well as rebuilding the drone and controller Docker containers to output more debugging and logging statements. This helped make sure that the A records for the session backends were being dynamically generated as needed. However, the information given back by all these methods proved to be conflicting and hard to parse. For example, dig queries would return successfully for type any records, while fail for queries of any other type. In the end, there were two key realizations to solve this problem. The first was that the DNS queries sent by the DNS provider of our domain were by default sent in UDP, as well as the queries sent by dig and NSLOOKUP. The second was to change the way the drone sourced its own IP so that it retrieved the IP of the EC2 it was on, rather than a private IP. This was done by creating an HTTP server to request the public IP of its EC2 from the AWS Instance Metadata Service and provide it to the drone agent. As a result of solving these problems, Mayfly was successfully able to connect and route to multiple drones, allowing the drones to be horizontally scaled in an EC2 autoscaling group. Lastly, we needed a simple automated process to deploy Mayfly through the Mayfly CLI. To do this, we use HashiCorp's Terraform and Packer to deploy infrastructure as code. This allowed us to simplify creating AMIs, provisioning security groups, elastic IPs, launch templates, EC2s, autoscaling groups, and more into a few inputs. To summarize all the things we talked about, I'll pass it off to Steve to finish by taking a look at the final architecture of Mayfly and the process a request goes through from beginning to end.
Thank you, Nate. So the process begins with a request for a session backend being received by Mayfly. A separate request is then sent from the Mayfly API to the NAT server. The plain scheduler is always listening for requests, and when one is received, it then returns a URL back as a response, while also scheduling an available drone to spawn a session backend through a NAT server request. When the URL is received by the Mayfly API, a database entry is created, and the URL is sent as a response to the original request. The drones are always listening for spawn requests from the scheduler, and when that is received, it coordinates with a Docker daemon to run the new session backend. Once Docker has the new session backend running, the URL sent to the user is now usable. When the user is directed to the URL, an external DNS provider routes the request to the internal DNS provider within the plain controller. This internal DNS server is then able to route the request to the corresponding drone hosting the session backend. The drone proxy receives the request and uses a built-in certification tool to confirm the HTTPS certifications of the request, ensuring a secure connection. Finally, once the connection has been validated, the user is connected to the new session backend via the proxy. And that's Mayfly. Thank you everyone for coming to the presentation. Now we'll open up the floor for questions. Please feel free to submit them through Q&A or chat.
All right, well, great job, everybody. Zach again. I see we have a couple of questions already. Okay. If a developer updates their application, do they need to update their container image in Mayfly? Nate, why don't you tackle that one?
That's a good question. For now, Mayfly doesn't support any automatic update of containers provided to it. What we could do to support that in the future would be to connect AWS ECR to Mayfly and a deployment pipeline from a GitHub repository. That would be a nice potential feature to add to Mayfly.
Yeah, it would make deployment of the images almost seamless, you could say. I see another question came in. Speaking of next steps, somebody asked, well, you mentioned JamSocket before, and there were differences between Mayfly. What could bridge that gap? What sort of features for Mayfly are you thinking of adding in the future? That's a nice question. How about Josh for this one?
Yeah, sure, Zach. I'd be happy to answer that question. So yeah, like I mentioned earlier, JamSocket does provide many session backend specific features that we would love to add to Mayfly. For example, JamSocket actually has a great metrics tool for observing the CPU and memory usage of each session backend throughout its lifecycle. And Plane actually provides the container image for this tool, and we would love to integrate that into Mayfly. And then one more feature we'd love to add is a loading page while your session backend is spinning up, because sometimes these applications they're going to be that take a little bit longer to load, and so we want to be able to signal to the user that they'll get to access their app shortly. So yeah, I'll pass that back to you, Zach. I do see a few questions in the Q&A.
Yeah, let's tackle those in order. An anonymous attendee asks, how does Mayfly handle errors with container deployment or configuration? Nate, you want to try that one?
Well, as Mayfly is currently, the user or the developer would be hosting their own containers not hosting the containers, but they would be putting the images onto Docker Hub or something like that, like GitHub Container Repository. And so Mayfly would deploy those to the cloud, but you wouldn't there wouldn't be any errors with container deployment necessarily. Yeah.
All right. Fred asks, how'd you come up with the name Mayfly? So that was Nate's invention, the idea behind it. So these session backends are somewhat short-lived, right? You spin them up when the user needs one, you spin them down, and Mayfly is a cute little creature that has a lifespan. We looked it up. How long was it? I don't know. Was it 1 day, or is that a dragonfly, or 3 days? And with the commands on Mayfly, you have to extend all metaphors. So in order to spin up, you hatch your session backend. In order to spin it down, you squish your session backend. So that was the motivation behind that. And somebody asked, what was your favorite part of building Mayfly? Steve, you want to step up and answer that one?
Yeah, sure. I think probably my favorite part might be I got a lot of experience with AWS. There's a lot of very frustrating experience, but I think in the end I got a much better idea of how EC2s work and some of the other services.
Okay, well, with that, I think we went through all the questions. So again, thank you everybody for coming out on a Friday afternoon and being in attendance live here for our talk. We hope to run into everybody in the future, and goodbye.